Hi, good morning, all of you. Dr. Nikhil here. Am I clearly audible? Yeah. So let us begin from where we left off yesterday. Till yesterday, we were done with the structural building part in the Gauss view. And after that, we had carried out the pre-optimization using classical mechanical model. Now, moving one step ahead, so as like I said, our today's objective is to carry out quantum mechanical optimization. So that quantum mechanical optimization will start, which is essentially the step number two for a computational calculation. So, okay, let us start with the molecule. So what I'll do, I'll take a little small molecule so that we can easily carry out the calculation and can proceed to the result analysis. Taking the giant molecule like the what we have designed yesterday, it will take around 3-4 hours to get computed. So I'll prefer to take a small molecule so that we can easily compute the result and can have a analysis part. So participant, take a small molecule like a methanol, ethanol, or any molecule of your choice and draw it on the drawing sheet. We'll do the computation of that molecule. So I'll take ethanol, I'll prefer CH3, CH2, and then OH. So quickly draw the ethanol molecule, and then as and when you are done, reply with the done. Quickly draw the ethanol molecule, and then as and when you are done, quickly reply with the done. So those who have joined little late, we have started the quantum mechanical optimization, which is the very first step toward any property mimicking. So under the optimization, the step number one, design the molecule. That is what we have done. We have taken the ethanol molecule, a pretty small molecule, so that we can easily complete the calculation within the session and then can check the result. We'll carry out the result analysis. So please draw the ethanol molecule. We'll proceed after that. Those who are done, reply with the done. Open a drawing sheet and draw the ethanol molecule. I can see Shivraj done. Very good. And there are two, three more participants who are done. Now, participant, let us quickly perform the pre-optimization. Pre-optimization, cleaning, or classical mechanical optimization. All three, four have the same meaning. Click on the brush-like option. Now, all of you would have noticed down that for this small molecule, even though we are cleaning or pre-cleaning it, there is no change in the structure. So note it down, this pre-cleaning or pre-optimization or classical mechanical optimization or vesicle level optimization, it mainly works for the big molecule. Small molecule, it does not have much of a stream. So I'm assuming all of you are done. Now next, we are moving toward the step number two of computational calculation. Step number one, designing the molecular structure. Step number two, design the input file. Now, this is a very crucial step. So please understand each and everything and then only go ahead. So step number two, design the input file. Input file for carrying out the quantum mechanical optimization. To do so, go to the calculate tab. To do so, click onto the calculate tab. And under calculate, you have an option of Gaussian calculation setup. Click onto it. Now, when you click onto the Gaussian calculation setup, a new window pop up like this. I hope all of you would have reached up to this. Now, this is a very important panel. This is a very important panel, and there are series of options which you have to understand. So, this is the first option. Participant now onto my screen because next few, I'll say maybe couple of hours, it is for the theoretical discussion. So over here, what is written? It is written as the job type. Job, it stands for calculation type. So whenever you see that there are computation researcher and they say that what is a job you would have done. So job in computational science named as a computation type or calculation type. So click over here. You will find that Gaussian will do series of calculation. It can predict the energy of the system by employing the Schrodinger equation as E psi is equal to H psi. It can carry out the optimization. That means can minimize the energy of your system by changing the molecular structure. It can carry out the frequency level calculation. Now, what does it mean by the frequency level calculation? Frequency level calculation means it will predict vibrational frequency or IR spectrum for your given molecule. Optimization plus frequency, that means parallelly it will do both the steps, optimization as well as the frequency. Now, a precaution. I never recommend to carry out optimization plus frequency in a single step because what we are going to do it, we are going to do the quantum mechanical calculation which are very heavy on even the supercomputers. So therefore, keeping two type of a calculation simultaneously, sometimes the calculation sees the error message or terminates in between. So better that you carry out optimization frequently one by one. IRC reaction coordinates. So when we'll move on to the reaction thermodynamics, we'll see the scanning option over there. Stability, leave that. NMR stands for the NMR spectrum calculation. So we will explore all of them one by one. I'll first start with the optimization. So click onto the optimization. And optimization is a computational step wherein the software will change the atomic positions of all the atoms we have seen. By changing their atomic position, it will eventually decrease the energy of the system. Now, how it will work, we'll see it in a meanwhile. The moment you click on the optimization, a few more panels comes over here. It says, do you want to optimize to a minimum energy or to a transition state? TS stands for transition state. So, participant, our objective is to optimize the molecular structure to its minimum energy or to a transition state. Our objective is to minimize the molecular structure to the minimum energy or to a transition state. Exactly, to a minimum energy. So I'll select the minimum.
Hmm.
Please click on to the minimum. Now there's a next option. So I am using the Gauss View 5.08 version. Some of you may be using Gauss View 6.0 something version. So therein this option would be different. Calculate force constant. So in my case, we have the never, once, always, and the read. In your case, it would be something else. So those who are interested to carry out the force constant calculation, see, I am sure all of you must be aware of that when we work on the infrared spectroscopy, for each and every bond, we have got a force constant value, K. F is equal to minus Kx. So if you are more interested to see the force constant value for each and every bond, then you keep this value as always. But if you have nothing to do with the force constant calculation, just keep it never. That way you will save your calculation time tremendously. Next, leave that RFO step. We'll see when we'll do the U-visible calculation. Let's come to the tight convergence criteria. Now, participant, before I enter into I have a default option. So default stands for never. Note it down. Default stands for never. Okay. When we need the force constant, see, we need the force constant calculation when we explicitly work on infrared spectrums. Because infrared spectrum, it has to do with the bonds stretching, bending, and then in this force constant calculation become meaningful. So right now for the optimization, we don't require it. So keep it never. Done. Now, participant, let us understand what is this tight convergence criteria. Before I come to the tight convergence criteria, let me explain what is the convergence criteria. Now, participant, understand how software perform the optimization. So we have certain molecular structure on our screen. Each and every atom, it has got certain Cartesian coordinates in a three-dimensional space. So what software is going to do it? The software will employ Schrodinger equation E psi is equal to S psi, and using the atomic coordinates given by us, it will predict the energy of the system. Now, next, what it will do? It will analyze the forces acting on all the atom. Participant, your time to answer the question. According to our type of calculation, which is the optimization, the software job is to minimize the forces acting on the atoms or to maximize the forces acting on the atoms. What should be the software approach? It should minimize or maximize the forces acting on all the atoms so as we'll reach to the optimized structure. Deepak says minimize the force. What about remaining participants? Exactly. So by minimizing the force, we will eventually reach to the equilibrium state of the molecule. And that is what we want to attain. So what software does? Participant, step number one, with respect to our given nuclear coordinates, software will analyze the energy of the system. Next, it will evaluate the forces acting on all the atoms. Depending on the direction of the force is the vector quantity. Depending on the force acting on the atom, it will do some atomic position changes. It will again evaluate the energy. Now, software sees, participant, your time to answer. Ideally, to reach the minimum energy configuration, The energy of the system should decrease or should increase. To achieve the minimum energy configuration, the energy of the step with each and every iteration, it should increase or it should decrease. Exactly, it should decrease. So what software will do? Software will see that with the change in the molecular structure, whether there is a change in the energy or not. If the change in the energy is in the decreasing order, the software is happy. It will again change the atomic coordinate depending on the forces, will again evaluate the energy. And it will keep on doing these iterations till it reaches a stage wherein the change in the energy become less than 10 raised to the power minus 5 Hartree units. I repeat, the software will keep on doing this iteration. That means change in the nuclear coordinate, again evaluate the energy, change in the nuclear coordinate, again evaluate the energy. It will keep on doing the same thing till the energy difference between the last two calculations become less than 10 raised to the power minus 5. At that stage, software will say, even though I am trying to change the molecular structure, but with the change in the molecular structure, energy change is very minimal. So therefore, we have reached to the minimum energy configuration. Participant, is this approach clear to all of you or not? Now, is this approach clear to all? Yeah. So participant, now where is the role of convergence come? Where is the role of convergence come? The role of a convergence come in terms of energy difference. Deepak says to please repeat. Deepak, see, have a look. All the participants, see, these things you need to understand. Otherwise, later on you will find it difficult. So what we have got a molecular structure onto my screen. This molecular structure, all the atom they have got certain atomic coordinates. Like this will have some atomic coordinate as in the xyz direction, and all of them will have certain coordination coordinates. What software will do? It will simply imply the Schrodinger equation, which is E psi is equal to H psi, and will evaluate the energy and forces acting on all the atom. Now let us say after the force calculation, software find that there is a net force acting on the oxygen like in this arrow. So what software will do? It will change the atomic position of the oxygen from here to here, will again evaluate the energy, and it will keep on doing the same thing till it sees that the energies keep on decreasing. Because what we want to achieve, attain the minimum energy configuration. The moment it reaches to a stage wherein the energy change becomes very bare, very near 10 raised to the power minus 5. Software says, even though I am trying to change the structure, but there is no significant change in the energy, that means we have reached the minimum energy configuration. Optimization done. Now, is this process clear to all of you or not? This will be done by the software, but you need to understand the process. Now, where is the process of convergence come? So we are over here, tight convergence. So what is the meaning of this tight convergence, participant? Convergence means something we are trying to narrow down. So what we are doing over here, even we are trying to bring down the energy difference after each and every calculation. That is what is the convergence. Now, what is the meaning of tight convergence? See, by default, what I said, the software will stop the calculation the moment it reaches 10 raised to the power minus 5. I repeat, the software will stop the calculation the moment it reaches 10 raised to the power minus 5 energy difference. What is this tight convergence criteria? When we define tight convergence criteria, the criteria changes to 10 raised to the power minus 6. So participant, now your time to think and answer the question. If I change this criteria from 10 raised to the power minus 5 to 10 raised to the power minus 6, what does it mean? Am I becoming too rigid or too flexible in terms of optimization? Moving from 10 raised to the power minus 5 to 10 raised to the power minus 6. Exactly. We are becoming too rigid over there, which means the calculation time will increase or will decrease. Increase. But what about the accuracy? The accuracy will increase or decrease? Exactly. So therefore, in computational science, we always say that there is a trade-off between the time and the accuracy. The more the time you will give for the calculation, the more accurate result you are bound to get it. So, sir, what does it mean? Shall we always select this tight convergence criteria? Participant, think logically. Ideally, we should apply this tight convergence criteria for a small molecule or for a big molecule. Exactly. In principle, we should apply this phenomena for the small molecule because bigger molecule will have an even more complicated mathematical equation. and will take Herculean amount of our time to get it solved. So generally, we employ this tight convergence criteria when the number of atoms within the molecule they are less than 8. Note down this value. When the number of atoms within the molecule is less than 8, only then we apply this criteria. Like in the present case, we have the total number of atoms as 4, 5, 6, 7, 8, 9. So even the ethanol molecule is big enough for this method. So don't select this tight convergence criteria, leave it as it is. So sir, does it mean that we are going to get inaccurate result? No, you will get accuracy up to 99%, but moving from 99 to 99.9, you have to pick up this option. So I recommend never ever select this option. Participant, is this tight convergence criteria clear to all of you or not? Great. Now let us come to the method part. Method. Now under the method, you have got first panel as ground state. There are Zindo, SIS, SAT, EOMS, CSG. Few more words are written. Leave them right now. Only focus on two words: ground state and TDSCF. TDSCF stands for time dependent self consistent field theory calculation. Don't get confused. SCF simply mean energy calculation. SCF simply stands for energy calculation. TD stands for time dependent. Sir, we are entering into the quantum chemistry or quantum physics. No, there is a single criteria to select either ground state calculation or TDSCF. Participant, listen to me because then series of questions will come. If you are trying to mimic a process which involves an electronic energy level change. I repeat, if you're trying to mimic a process which involves electronic energy level change, select TDSCF calculation. But if you're trying to mimic a process which does not involve electronic energy level changes, go with the ground state calculation. Now, keeping this objective, answer me the question. Right now, we are performing optimization calculation. Does optimization calculation require electronic energy level changes? No. So therefore, we need to go with the ground state calculation. Sir, a little bit more. Participant, consider that your objective become to predict the infrared spectrum of the given molecule. To predict the infrared spectrum of the given molecule, I should go with the GS calculation or TDSCF calculation. Think about now. IR spectrum calculation. Del incorrect. Infrared spectrum. Does it require electronic energy level change or vibrational energy level change? Exactly. For the vibrational, Ravina, please correct. Electronic energy level, no. It is the vibrational energy level which changes when we bombard the molecule with the infrared photons. Is this clear? So therefore, for vibrational or for infrared spectrum calculation, you need to go with the ground state calculation. Next, participant, if your objective become to predict the U visible spectrum, for the U visible spectrum, I should select the ground state or TDS here. I am discussing few case studies because those things we have to cover. Ground state or TDS here. Shivraj, be careful. U visible spectrum calculation. When you bombard a molecule with the U visible photon, that involves a electronic energy level change or vibrational energy level change. Exactly. So that involves electronic energy level change. So therefore, in that particular case, you require TDSCF calculation. Participant, next question. NMR spectrum calculation. For NMR spectrum calculation, think about does it require energy, electronic energy level change or not? So in that case, ground share or TDSCF, NMR spectrum calculation. Exactly, nuclear energy level and no. Sharad, incorrect. NMR, does it involve electronic energy level changes? No, it does not involve electronic energy level changes. It has to do with the polarization. So therefore, again, ground state energy calculation. Participant, have a look onto my screen. So if I select NMR over here, under the method, you won't be able to see the TDS here because NMR calculations are performed at a ground state level because no electronic energy level change. I'll revert back to the optimization and come back over here. Participants, few more case studies. If your objective is to predict the fluorescence and the phosphorescence behavior, ground state or TDSC, exactly, because fluorescence and phosphorescence, they are the de-excitation process, de-excitation from upper electronic energy level to the lower electronic energy level. So that case, TDSCF. Participant, next one. If you want to predict the interaction energy between ethanol and a water. So if I keep a ethanol and a water molecule in a single window, and my objective become to predict the interaction energy or the hydrogen bonding, it's going to be TDSCF or GS. Think about practically. You have a bottle of a ethanol, you have a bottle of a water. When you mix them both, on mixing, the electronic energy levels will change or they will not change. Exactly. The correct answer is ground state because the electronic energy levels will remain still same, the ground state, but the energy of the ground state will change. Is this point clear to all of you? The molecule will still remain in the ground state, but the energy of the ground state will decrease. Is this point clear? Exactly. So in that point, so therefore interaction energy studies calculation. See, we are going to do that. Absorption phenomena, participant, absorption, ground state or TDSCF. You have got an adsorbent, adsorbate, they interact with each other. They interact with each other. So in that particular case, TDSCF or ground state. Are participant, think about that. You have got an iron, a surface of an iron, and onto the iron when an oxygen molecule interact, then what will happen? Ground state or TDSCF? Exactly, it's going to be a ground state calculation because therein the energy of the ground state will change, but not the energy level will change. It will not go to the excited state. I hope now these things would be clear. So I'll go with the ground state calculation for the present case. And now I'll come back to this point. So again, this is a very important point. Before I switch on to this particular panel, I hope all of you are able to see certain keywords written over here. Hartree Fock as in HF, DFT, MP2, CCSG, and so and so on. So participant, before I enter into the technical part, there is a one quick question. Out of these many words, which word you have seen frequently in the manuscript? Is it HF, DFT, MP2, CCSG, or something else? Which word you have seen frequently? Exactly. All of you see you are replying with a DFT. Now, we need to understand why DFT. Participant, next 10 minutes, theoretical part. So I can go to the slides. Otherwise, I don't require the slides right now. So I'll have a vocal discussion preferably. So participant, what are these things? Note down, they are called as the theory level. Participant, before I enter the next part. So there are few words. What is this optimization? It is the calculation type. What is this method? It stands for your calculation type. Again, what does this keyword stand for? They stand for the theory type. So if somebody asks you what type of a calculation you had performed, so you need to answer optimization, frequency, scan, NMR, and so on. If somebody asks you what type of a theory level you have taken, don't answer ground state, TDSCF, optimization. Then they would like to know whether you have employed HF, DFT, MPD, or CCSG. So be particular about the words. Now coming back over here. So what are these things? They are the theory level. Sir, what is the theory level? I'll simplify. So participant, we have a principal objective, the solution of the Schrodinger equation. E psi is equal to H psi. Now, participant, ask you one question. If I ask you a value of a 1 by 1000, all of you will quickly reply, sir, it is 0.001. And I'll quickly confirm that it is correct. But now, if I'll ask you one value of 1 by 999, triple nine, tell me the value of 1 by 999. Participant, 1 by 999, 1 divided by triple nine. Now, that takes up a time because you will need a calculator to solve it. But can I say that the value of a 1 by triple nine or 1 divided by triple nine will be approximately equal to 1 by 1000? Can we say like this? Yes. And that is what it is called as the approximation. This is what it is called as the approximation. Participant, now understand the concept. So we had an objective to solve the Schrodinger equation. If we solve it without using any approximation, it will take Hercules amount of our time. So therefore, long back, different theoretical researcher group, they came up with the different approximations. Now you don't have to enter into the what approximations they had used, but you need to know how these models differ from each other. Principally, they have the same objective is to solve the Schrodinger equation, but they all uses different approximations. What approximation? Leave that. Now note down as we are going down in the list, that means moving from molecular mechanical to Hartree Fock to DFT to NP2. MP2 stands for molar closet, the two person who had conceptualized the calculation. Then CCSD couple cluster calculation. As we are going down in the list, the approximations used in the solution of Schrodinger equation increases. You need to remember this. As we are going down in the list, approximation increases. Participant, your time to answer the question. So accordingly, out of DFT, MP2, and CCSG, which model will provide you highest accurate result? HF, DFT, MP2, and CCSG. Exactly, because CCSG has least approximations used. So accordingly, which theory type will take least amount of time to provide you the result? HF, DFT, MP2, or CCSG? Exactly. That is why HF calculations are very fast. So accordingly, if I am working with a giant molecule, I should employ HF calculation or CCSG calculation. Exactly. Giant molecule already showing a equation is very rigid, very tough. So in that particular case, don't apply the CCSG model. You need to apply the HF model. Participant, a quick difference between HF, DFT, MP2, and CCSG clear to all of you or not? There are few more things we have to discuss. Participant, now comes the question. Sir, how do we decide which molecule is big, which molecule is small, which model is to be applied for which one? So participant, there are rigid conditions we need to follow. Now listen to me. The CCSG models you need to apply when a molecule on which you are working comprises of less than or equal to 8 atoms. I repeat the condition. If a molecule consists of less than or equal to 8 number of atoms, only then you can employ CCSG model. If you apply the CCSG model for a bigger molecule, the calculation will terminate in between without any result. Sorry. Similarly, MP2 or MP4 calculations are usually employed when a molecule consists of 8 to 80 number of atoms. 8 to 80 number of atoms. Not less than 8 because then CCSG can be applied. Not more than 8 because more than 80 equation become too trouble and approximations are less. Similarly, DFT models are usually employed for molecule 8 to 80 number of atoms. 8 to 80 number of atoms. So we are talking in terms of number of atoms. DFT is usually employed when the number of atoms within the molecule stands from 80 to up to 400. 80 to 400. Similarly, HF, even bigger molecule, 400 to 500. You can even go up to 600 as well. So condition, CCSD up to 8 atoms, MP2 or MP4 calculation, 8 to 80, DF2 80 to 300 and 400, Hartree Fock 400 to 600. Now, participant, I want all of you to think about your own research based molecule, and reply in the chat box which theory level you think is more apt one. Is it the CCSG, MP2, MP4, or DFT? And that is the see, all of you see your reply, you are replying with a DFT, and that is the reason all of you are seeing DFT gaining lot of importance in the manuscript. Is this one clear why DFT is gaining lot of importance?
If we have any HPC, then we can use CCSD. Na?
Pardon, say it again.
If we have any HPC, high performance computer, in that case, can we use CCSD?
I am talking about only high performance computing resources only. So these things are applicable for HPC. On laptop, if you will try the CCSD calculation for every other molecule, it will fail. Is this clear?
Yes.
So now
If we
participant,
have any workstation, then we can use. Na?
see workstation are even less as compared to your supercomputer. So if I'm avoiding the CCSG calculation or supercomputer, think about workstation will be very, very difficult. So therefore, CCSG calculation you only employ when you see that your results are not accurate enough with a DFT, and that will not be the case generally. So CCSG models are generally employed when your results are not accurate enough with the DFT models. Okay. So where I was, participant. Now you need to think even more critically. What exactly it means? See, I think 2 years before, there was the one participant who had asked a very good question. The question was, see, she was working on a complex. Understand the question, please. The complex was nickel chloride, tetrachloride, NiCl4. Charge was 2 minus. Now, participant, think about. You have got nickel tetrachloride and CH4. There are two molecules. The two molecules have same number of atoms, 5 and 5 each. But the Schrodinger equation for both of them is going to be similar or it's going to be different. Both the molecule have same number of atoms, nickel tetrachloride and CH4. Exactly, they are going to be different because Schrodinger equation it is dependent on number of electrons, number of protons in the atom. So therefore, think about for nickel tetrachloride, the Schrodinger equation is going to be more complex or less complex as compared to CH4. For nickel tetrachloride, exactly, it's going to be a more complex. So therefore, participant, now we have to modify our previous criteria. Our previous criteria was you need to apply CCSG model when the number of atoms are less than 8. We are adding one more condition over here. The one more condition, none of the atom should have d orbital filled or vacant whatsoever. Therefore, CCSG models are applied only when the number of atoms are less than 8 and none of the atom has filled or vacant d orbital. Likewise, MP2 or MP4 models are applied only when the number of atoms are less than 80. And there is a one more condition, none of the atoms should have d and f orbitals filled or vacant whatsoever. Similarly, DFT. Now, with the DFT, there is no such limitation. DFT you can employ even with the presence of d orbital or absence of d orbital. Similarly, Hartree-Fock, presence or absence whatsoever. So, participant, now think about for an ethanol molecule, which we are seeing on our screen, for an ethanol, which model I should apply? Is it going to be CCSG, MP2, MP4, or DFT or HF? The total number of atoms are 9. So which model is going to be the more apt one? Exactly, it's going to be the MP4. MP2, MP4, anyone you can apply. MP4 is more accurate as compared to MP2. As like I said, going down in the list, accuracy increases. So you can either apply MP4 or MP2. That is up to you. Now, participant, next question. Next question. For a ethanol, I can apply MP2 or MP4 calculation. What if I substitute oxygen with the sulfur and I convert it into a thiol? Is it still MP2 MP4 I can apply or I need to have different purity level? If I substitute oxygen with the sulfur, no, because sulfur consists of Naishara. Think about one more time. Think about one more time. Exactly. I need to switch on to the DFT model because see, sulfur, it has got d orbital. Although they are not filled, but it has got the presence of d orbital. So therefore, you need to avoid the NP to NP4 CCSG model. So you are left with only DFT model. Is this point clear to all of you? How to make a careful selection between all the four models? Is this point clear to all of you? How to make a selection between all the four models? Ashok says no. Ashok, see, replacement of oxygen. Ravina says repeat. See, Ravina, right now we have 9 number of atoms within the molecule. With 9 number of atoms, I cannot apply CCSG. I can only apply MP2 or MP4 model. Now there is a limitation with the MP2 MP4 model. Limitation is even though the number of atoms lies within 8 to 80 zone, but they have a one more condition. None of the atoms should have d orbital, whether filled or vacant whatsoever. Now, if I look at this molecule, ethanol, carbon, hydrogen, oxygen, none of the atoms have the d orbital. So I can safely apply MP to MP4 model with the replacement of oxygen with the sulfur. Now, sulfur, third period element, what it has? It has got a vacant d orbital. So, with the introduction of a vacant d orbital, I cannot apply MP to MP4 model. Ashok, Dr. Ashok and Ravina, is this now clear? So conclusion, don't just look at the number of atoms. You need to see the number of d orbitals as well. Ashok says why? Ashok, think about how many d orbitals we have it in a typical shell of the atom and how many s orbitals we have it in a typically atom. Think about in a given shell of an atom, how many s orbitals we have? Only one. And what about the d orbital? We have D as the five orbitals. So therefore, the number of five orbitals, when it increases, the mathematical equation become too trivial to get it solved. So therefore, we cannot imply NP to NP4 CCSG model. Is this clear now, Ashok? And if you think about the f orbital, they are even seven number of orbitals. Seven orbital mathematical equation become even more difficult to solve. So less approximations will not work over there. You need to find even more approximated models. Great. So participant, where I was, one more thing I need to calculation will become very difficult. Now participant, one more thing I would like to emphasize over here because these things we are observing in the manuscript and that becomes the ultimate reason for the rejection. What exactly is that? Participant, can I apply DFT model for the ethanol molecule? Answer me the question. Can I apply the DFT model for the ethanol molecule? Yes, I can apply because there is a condition that the number of atoms should be less than 400. Yes, I have it. None of the atom, no, that none of the thing is exactly, but it is going to be less accurate. So what we are observing it in few of the manuscript which comes to us for the review part. Please share free document for the selection for the self study. They are on the Google Drive. I'll show you right away. So where I was in few of the manuscripts which came to us for the review part, what people are employing, they are employing less accurate models. They are employing less accurate models for the molecules on which we can even employ more accurate model. Like as in the particular case of ethanol, we can simply apply MP4 model. That if somebody applies DFT or HF, we need to reject the manuscript or put it for the main for the major revision. Is this point clear to all of you? That don't just randomly select the models or theory level. Look at on your own molecule and then decide which theory level is the most apt one. Is this clear? Great. So now I'll show you something on the Google Drive. See, I am not pressing that presentation mode. Presentation generally it becomes very boring. So I'll show you those slides. Maybe you can look at it after the session. So we have these slides, the application of computation chemistry. What I had explained just now, it is over here. Yeah. It is over here. The HF, MP2, DFT lies in between HF and the MP2. These are the published results in some of the journal. So HF, MP2, CCSD, CCSD2. As we are going down in the list, the calculation time increases. Do all the approximations models are in the other software like VASP and Quantum Espresso? Yes. See, the approximation lies in the theory model. The approximation lies in the theory model. So they are same irrespective of whatever software you are using. But now we have emphasized like on the VASP and the quantum espresso. Note down, VASP and quantum espresso, it does not perform only DFT calculation. It works on plane wave DFT calculation. So therein you have even more number of approximation. Is this clear, Deepak? VASP, quantum espresso, it works periodic or plane wave DFT calculation. So slightly more number of more approximations. Great. So participant, maybe if you find a time, you can just have a look onto that. Going down in the list, the value of these functions increases, which mean calculation time increases, which mean accuracy increases, which mean approximation decreases. Then you can have a look on this published research article wherein people said number of atoms, if it is less than 8, you can apply cluster model or couple cluster model. The moment you are reaching in the stage of 82 up to 400, you can apply DFT model. Hartree Fock comes after that. I'm leaving it to all of you to just have a look onto it. I'll not enter the presentation mode. There are few more softwares which you can use except than the Gaussian. I think Gamma's free software, Spartan free, NWChem free. I think remaining softwares are they are mostly free, but they have a limitation. The limitation is they are not easy to operate. They don't have the graphical user interface to operate. So that is the majority of the researchers they prefer the Gaussian. Now I'll close this and I'll come back to this calculation type. So I'll go with the DFT model because DFT model I'll first give it a check. If my results are not accurate enough, see I can apply the MP4 model, but I'll first try with the DFT model. If my results are not going to be accurate enough, then I'll switch on to the MP4 model. Sir, how to check the accuracy? Wait, we'll learn that. Now, participant, next thing. So you have got something related to the unpaired electron in the system. So note it down. If you are working with a system wherein you have got unpaired electron, go with the unrestricted type of the calculation. If you are working with a system wherein all the electrons are paired, if all the electrons are paired, go with the restricted model. If you are not sure whether in your system the electrons are paired or unpaired, leave it default. The software will predict it automatically and will do the calculation for you. So my recommendation, always keep this option as a default spin, because for giant molecule, you never know whether the electrons are paired or unpaired. Let it be default spin. Software will automatically do the job. Now next, this is the important point. Have all of you reached? I am going very slow because we have a lot of theory to understand. Have all of you reached? Now, participant, what exactly is this? This is a list of functional. This is a list of functional. So before I enter into the theory part, a same question I'll ask, sir, if sulfur exists in the compound. So if sulfur is there, I cannot apply MP2, I cannot apply MP4, I cannot apply CCSG model. I am bound to use the DFT model. Is this clear? Okay, participant, can I put a one generalized statement? The statement is MP2, MP4, and CCSG models, they are applicable only for the period 1 and period 2 elements of the periodic table. Can I generalize like this? The MP2 and MP4 and CCSG model, they are applicable only for the period 1 and period 2 elements of the periodic table. Think about that. Think. Yes. So if zinc, copper are there, definitely you cannot apply MP2 or CCSG. You have to apply only DFT model. So period 1 and period 2 element, they don't have the presence of d orbital. So therefore, only then you can apply MP2 and CCSG model. Uh, I think I have closed the presentation. Okay, leave that. So participant, now coming back over here, this is the functional. Now, what is the functional? I'll explain like the way I explained the theory level. But before that, there are few keywords written over here. Please answer in the chat box. Out of these functional, which functional you have seen frequently in the manuscript? See, all of you are working in a different institution, different research phase, but your answer is same. It's B3LYP. Now, why B3LYP? Why not others? That is what we need to understand. So before I explain what is this B3LYP, let us understand what is the functional. Participant, for a given atom, for a given molecule, you have got atomic orbitals or molecular orbitals. Now, answer me the question. The shape of these molecular orbitals, as in sigma, sigma star, pi, pi star, and non-bonding orbital, they are same or they are different from each other. Exactly, they are very different from each other. Sigma along the internuclear axis. Kriti says to repeat. Kriti, you have got the sigma orbital, pi orbital. Their shapes are same or different? They are different. So to explain the shape of these molecular orbitals, we have got something called as a functional. Sir, not clear. Participant, if I have to draw a straight line on a paper, I have got a mathematical equation as y is equal to mx plus c. Am I correct? Similarly, if I have to draw a circle, parabola, hyperbola, ellipse, we have got certain mathematical functions. Like the way to draw the molecular orbital shape, you have got a functionals. We have got a certain function which we call them as a functional. So is the meaning of functional clear to all of you? Functionals are the mathematical function which define the shape of the molecular orbital. And why we are using, because shape of each and every molecular orbital, they differ from each other. Is the meaning of functional clear to all of you? Great. Now see, there are series of functionals. There are series of functionals, and in the literature you will find even more than that. So sir, which functional we have to use? So, like the way we have a rigid condition in terms of which theory level we have to use, similar conditions we have it over here. What are the conditions? Participant, listen to me carefully. Give me a minute. Now, coming back over here. So this is B3LYP, and then you have got omega B97XG. You have got CAM B3LYP. So these are the three most often used functional. And out of the three, we generally go with the B3LYP. Now, why B3LYP? See, this B3LYP functional, it was introduced by a group of four scientists, Bacon, Lemon, and then there were two more. I am forgetting their name. So their functional we use when a molecule on which we are working comprises of s orbitals, p orbitals, even empty d orbitals you can take. Huh. By the moment you enter into the filled d orbitals or filled f orbitals, vacant f orbital, then you don't take B3LYP. Then you go with the omega B97XD, a more accurate one. I repeat the condition. If you are working with a molecular system wherein atoms comprises of only s, p, or vacant d orbitals, not the filled one, you can safely select B3LYP. The moment you enter in a zone wherein the filled d orbital, partially filled d orbitals are there, don't go with the B3LYP. Go with the omega B97XD. Participant step by step. For ethanol, B3LYP or omega B97XD. Ethanol, B3LYP, omega B97XD. Exactly, B3LYP because carbon, hydrogen, oxygen, none of the atom has filled d orbital. So I can simply think, not understand. Ashok, see, over here you just have to look whether do you have d orbital or not. So if the d orbitals are there and if they are filled, don't go with the B3LYP. If they are filled, go with the omega B97XD. So ethanol, carbon, hydrogen, oxygen, none of the atom has filled d orbital, so I can simply select B3LYP. Participant, think about your own research-based molecule and answer me in the chat box B3LYP or omega B97XG. So two participants have replied with the B3LYP, one with the omega 9. What about remaining participant? Think about your own research-based molecule. The B3LYP will be applicable or omega B97XG applicable or what does both? Now, say as like I explained, going down in the list, approximation decreases, calculation time increases, accuracy increases. So whenever you have the d orbital presence, you need less approximated model, omega B97XG, and then the calculation will increase. Is this clear, Kriti? There are so many functionals. You can use whatever you want to use it. See, there are so many functionals. You can use whatsoever you want to use it. I am emphasizing on those functional which are widely applicable and used in the literature. Omega B97XG, Omega B3LYP, and Omega B97XG. I think remaining participant they have not either understood the condition or they are little bit confused. See, B3LYP, check the atoms in your molecule if any of the atom has the filled d orbital, leave B3LYP. You need less approximated model, omega B97XD. If none of the atoms has the filled d orbital, safely you can go with the B3LYP. Now in the chat box, reply B3LYP or omega B97XD for your own molecule. So Devraj, omega B97XD, Ravina B3LYP. See, these things you have to fix. before you switch on to your own calculation. Del says B3LYP, and that is the reason in literature you find B3LYP is being frequently used. Participant, next question. If my objective is to study the metal complexes, coordination complexes, B3LYP or omega B97XG, coordination complexes. Exactly, because therein you have already got the metal ion. Metal ion definitely it will have the presence of d orbital. So in that particular case, you are bound to use omega B97XG. So like that, you have to decide. So I hope functional thing is clear to all. So I'll go with the B3LYP as I'm working with the carbon, hydrogen, oxygen only. Participant, next thing, a basis set. What is the basis set? Participant, before I enter into the calculation type, answer me the question. So we have got sigma orbital and pi orbital. If I apply an electric field along sigma orbital, metal or enzyme, the moment you enter metal generally you take sodium plus, magnesium plus, calcium plus, and so on. All these sodium, magnesium, calcium, they have the presence of d orbital. Now for sodium and magnesium, metal ion, they does not have the filled d orbital. So you can safely take B3LYP. The moment you enter into the potassium plus, calcium 2 plus, you have got unfilled d orbital. D orbitals are there, but they are also filled. So in that particular case, zinc, definitely dear D10 configuration. Zinc D10. So omega B97XG. Clear, Kriti? Unless and until d orbitals are filled, you can take B3LYP. The moment it gets filled, you cannot take B3LYP. So participant, what is this basis set? We have got sigma orbital, sigma star orbital, pi star orbitals. Now these molecular orbital, if I subject them to in the external electric field, think about if I apply an external electric field to all these molecular orbital, they will get polarized. Am I correct? They will get polarized. Am I correct? Yes. Now the polarization of sigma and pi orbital are the same or different from each other? The polarization of sigma and pi orbital are the same or different from each other? Exactly, they are different from each other. So to explain the polarization of these molecular orbital, we have got something mathematical named as the basis set. Is the relevance of basis set clear? The basis set is a set of mathematical equation which explain the polarization of these molecular orbital. Clear? A basis set is a set of mathematical equation which explain the polarization of these mathematical orbital. Now, participant, along with the polarization, you have another thing which is called as diffusion. So I'll take it little simpler. You have got s orbital and p orbital. Out of s and p orbital, which is more diffused in nature or more diffused in shape? Is it s or p orbital? Exactly. Similarly, when you move from P to D, it becomes more diffused. D to F even more diffused. Similarly, you have got sigma and pi orbital. Sigma orbitals are more diffused as compared to pi. So therefore, to explain the diffusion characteristic of these molecular orbital, we use basis set. So basis sets are used to define diffusion as well as the polarization of these molecular orbital. Is this basis set concept clear to all of you or not? Basis set simply a set of mathematical equation which explain diffusion as well as the polarization. Now, participant, I'll click over here. There are series of basis set and number of basis sets are there. May I know out of these many basis set, which basis set you have seen frequently in the literature? There are so many basis set. Which one you have seen frequently in the manuscripts? So again, see the same thing. All of you belongs to different institution, different research area, different manuscript, but the answer is same. It is 6311G or 631G. Now, what is so special about this 6311G? That is what we have to understand. So, participant in literature, you will find people would be using either 631G or 6311G or LNL2DZ, LNL2MB. I am coming to that. LNL2DZ or LNM2B. Now, sir, what are the conditions for the selection? Participant, note it down. If you are working on a molecular system wherein all the atoms are covalently linked to each other, then you can simply take 6311G or 631G. The choice is completely up to you. If you are working with a system wherein all the atoms are not covalently linked to each other, then you require more accurate model, which is LAN or LAN L2DZ or LAN L2MB. Participant, think about ethanol, 631G or LAN, ethanol, 631G or LAN. You need to check the bonding characteristic of the molecule. If all the atoms are covalently linked, you can simply take 631G. If all of them are not covalently linked, then you have no other choice. You need to go with the LAN. I did not get, sir. See, look at the molecule of ethanol. Wait a minute. In ethanol, all the atoms they are linked covalently with each other. Oxygen, hydrogen, sigma bond, oxygen, carbon, sigma bond, carbon, carbon, sigma bond. So all of them are connected with each other via some sigma and pi bond. So if all the atoms are connected by sigma and pi bond, simply you can take 6311G or 631G. But if all the atoms are not covalently linked, you have no other choice. You need to go with the more accurate model, LAN L2DZ, LAN L2MB. So now think about the ethanol. Which basis set I should select? 6,3 or LAN? Exactly. Participant, next question. If you are working on coordination complexes, metal complexes, LAN or 6,3? Exactly, because therein you have the presence of coordinate bond. Similarly, participant next. See, I'll discuss few more case studies so that these things become more clear. If my objective is to study the interaction, exactly, if my objective is to study the interaction between water and the ethanol, that means the hydrogen bonding, LAN or 6,3, exactly, because hydrogen bonding does not comprised of sigma and the pi bond. It has got certain other type of interaction. So that's how you have to decide which basis set you have to select. Participant in the chat box. Now think about your own research-based molecule. 6,3 or LAN. Great. So I can see majority of you are replying with the LAN. That means you would be working with a system wherein all the atoms are not covalently linked. So make a careful selection. Okay. So present case, I'll take 6311G. I am done. If you take LAN, participant, have a look. If you take a LAN, then you don't have to select remaining option. LAN automatically comprises of remaining option. But if you are taking 6311G, I recommend all of you to always take plus D and P over here. Now, when I was learning this computational chemistry, I got confused. If the system is macrocycle, see in a macrocycle, all the atoms are covalently linked to each other. You can simply take 6311G. Clear, Sharat? Great. Participant, whenever you are working with a 6311G, always take plus. Why plus? Because the diffusion and the polarization, they are distance dependent property. D and P. See, when I was learning this computation chemistry software, I got confused that this D and P stand for the d orbital and p orbital. Nothing like that. It stands for diffusion and the polarization. So if you are working with the periodic table, second period and third period element, single D and single P is sufficient. If you are working with a lanthanide or actinoid heavier element, then you need to select 2D, 3D, 4D as well. So right now I'll go with the D and the P model only. Are all of you done up to this? So participant, I can feel time is almost elapsed. I'll put up a quick summary. In a quick summary, Ashok, I'll recommend to please follow the recording. So where I was over here. Quick summary. We looked at what are these type of calculation. Difference between plus and plus plus. Plus is applicable for short range correction, double plus plus long range correction. So unless and until you are working with a lanthanide or actinoid, don't take double plus. Lanthanide or actinoid, double plus. Otherwise, single plus. So where I was over here. Quick summary. Optimization, we had looked what is the optimization. Then we understood this concept of transition state, minimum energy. Then we understood the concept of force constant, tight convergence criteria, 10 raised to the power minus 5, 10 raised to the power minus 6. Then under the method, ground state, TDSCF, fluorescence, phosphorescence, out file reading, when we will learn, sir. We'll learn on day number 3, that means tomorrow. Today we are right now on to this calculation panel. That is what I said. This panel is very important. Otherwise, will become very challenging later on. So where I was, yeah, then we understood what are different theory levels, the approximation used, calculation, coordinate, and then criterias, presence of d orbital, filled d orbital, unpaired or paired electrons, then the different functional molecular orbital shape, which one is more optimal one, presence of d orbital, filled one, then non-bonded bonded interactions, and that's it. Tomorrow I'll take all of you toward this charge in singlet. If I have a mob structure, should I use double plus or plus? Single plus is more than sufficient because in MOF generally we don't have the actinides and the lanthanides. Radioactive elements, unless and until you are taking, take only single plus. Okay, participant. Now we are completing the session. So where I was, hmm, this charge in singlet we'll see in the tomorrow session. Up to over here we are clear. Why is it so? Because see, the moment you are entering into the lantern and the actinide, you require less approximated model. You require less approximated model. Less approximation mean little down. Sir, how to have the access of the Google Drive? You don't have the access to the Google Drive. How come? Participant, I hope today's session is clear to all. Please practice, listen to the recording because we have covered a lot of theory part. Understand it from the recording. If in case you have doubt or would like to learn one more time, join in the evening batch today at 7 p.m. The same link will be applicable. Let me share this Google Drive link one more time so that who don't have the access, they will click onto the link and can click onto the request access. I'll approve it. I can see that there is no pending request on my side. Uh, I don't know who had asked the access point. They'll click onto the link and click onto the request access. I'll approve it maybe in half an hour. So participant, with that, we'll take a leave. We'll meet up today at sharp 7 p.m. Those who would like to repeat. Otherwise, tomorrow morning at 11 a.m. I'll put up the recording by 1 a.m. Is the session clear to all? Is the session clear to all? I'll keep it here. Yeah. So please practice. Please practice. Few more research articles. Look at the systems they would have used. Look at the system they would have used and justify whether their correct theory functional basis set is the correct selection or not. Cancel. Thanks to all. We'll meet up tomorrow at sharp 11 a.m. Stop share.